Today we are doing the Aftershocks Masterclass, and the cunning plan is that I'm going to start with the physics, and then at no later than 8 o'clock, and I'm determined that I'm just going to stop if I haven't finished everything I wanted to do by then. I will, if with your permission, pitch to you my own course, because that's how I make my living. But you, at that point, if you are finished, you're not interested in investing in tutoring, then you can leave and no one's going to mind. Okay. The last time I did this was quite a long time ago. It was the end of October. I haven't done one for a very long time, because in the last one some people misbehaved. They just were sending inappropriate messages. We have a zero tolerance on inappropriate messages. You will not get a warning if you send something that's rude or even slightly not right for this environment. Then you're going to get kicked out. Meg's on it. She's on it. So yeah, can you see? If we get interrupted by the dog, it's because he's in here with us. Well, one of them.
He's left.
Oh, has he?
Yeah.
Oh, well done. Okay, so that's all right. So, so without further ado, we're going to get on, and I'm going to share my screen. Hopefully this is going to work again. Cool. I hope this is going to work. Yes, there we go. Okay, so what is going to be covered in the session today? If you've been to one of these before, you will not recognise it because it's completely different. So we're going to talk about how to read any question so that you know how to hit exactly what's on the mark scheme. Everybody says that they understand the physics, they just can't answer the questions. And that comes up so frequently that I have invented a whole method of explaining to you how you can read any question so you know exactly what to put. There's going to be a session on how to effectively revise. Spoiler alert, you don't revise. I will explain that. If you've not been with me before, you might have some idea if you've been with me before, but if you've not been with me before, you might be surprised by a teacher saying, don't revise. But I really, really think you should do something much more effective instead. So this is then how you improve your grade. I have promised everybody that turns up to this session that they can have a work plan that is specific to their year, specific to their exam board, and those will be being issued in that how to plan your preparation for your summer exams, whether they're year 12 exams, end of year 12 exams, really important year 12 guys, because you need your predicted grades so that you can apply to UCAS in the autumn of your year 13, or of course the real thing for the year 13s. You've got to plan your preparation, and you really need to start now, and you will find out why when we do that bit. When we've done all of that, if there's any time, I might do a few multiple choice questions on how to improve your odds. That bit, multiple choice questions on how to improve your odds, is at the moment on my free stuff page of my website. So I've got two other masterclasses there. One is called the Autumn Accelerator and the other is called Cheat Codes. Those two masterclasses do include stuff on how to improve your odds in multiple choice questions, particularly useful for AQA because the AQA course has so many multiple choice questions. And then we're going to have a bit of advice for parents, just so that you know what you can do to help your child, because A-level physics is hard. It's fourth hardest. The only things harder are Latin, critical thinking, and further maths. So of all the A levels, this is the fourth hardest one you could have picked. That doesn't mean it was a bad idea. A-level physics will open so many doors for you, it's unreal. So it's a really good idea that you've picked it, but you have to recognise that it's hard. Okay, after that, like I say, I might be sharing with you, I've got a really good special offer that you might be interested in, but I'm not going to talk about that now. Right. So the first thing is then how to read any question so that you know how to hit exactly what is on the mark scheme. And I call this my ninja question reading, basically you spent the last 17, 18 years of your life learning how to skim read, and you cannot afford to do that in your exam. And I'm sure your teachers have said to you, you must read the question. You've got to read the question. And you go, I did. I read the question. I read it really carefully, and I still got it wrong. So the thing is that nobody teaches you how to read the question. The very first thing you've got to do is you've got to slow down. And the next thing you've got to do is you've got to notice the right things. So the ninja question reading, I have explained it before. Again, there's a free bit on my free stuff on my website. Go and watch the 13-minute video on ninja question reading, how to make sure you slow down. It involves a highlighter pen. But I want to demonstrate it today. So this is an example of how to do ninja question reading. So this is the bulk of it. This is how you read any question, because this thing is the thing that most people can't do. Okay, they can do the physics, they understand the physics, they understand the concepts, they understand the equations, they just can't answer the questions. And it's like, there's a disconnect there. I read the words and I still don't know what to do. So it's just that one thing. If you can get that today, your grade will be better tomorrow. So let's see if we can demonstrate how to do ninja question reading. Right, so I have got some examples. We're going to do ninja question reading with an OCR paper. Then we're going to look at clues. Again, it's really part of the ninja question reading. Year 12 are going to do a year 13 question. Oh, yes. And then some questions you need to learn by heart. There are one or two that for sure are going to come up. I'm going to give you an example of one. And then the last one that comes up every single time is describe an experiment to show. And you can see that the example that I've got there is from June 2011. So it has, it's obviously been around for a very, very long time, this question. In fact, it's not new. Okay, okay, so describe an experiment to show questions. I'm going to, hopefully I'll get through all of this. Right, so we're going to start off with OCR A, paper 1. Let's see if that one works. Oh, I've got an error.
I have a question.
Oh, a question, go on then.
Someone asked, if critical thinking is so difficult, why do so many universities not accept it?
I think because it doesn't give you enough content stuff. So yeah, it's just I'm going to have to stop sharing this in order to find my file, which is really annoying. I apologise. Yeah, so critical thinking is not accepted simply because there's not enough knowledge with it. And even though we shouldn't do that, we shouldn't judge things by the knowledge, just the facts that we learn. It's true that nevertheless that people do that. So yeah, I agree with you. It really ought to be accepted. Right, hopefully you can see question 19 from the OCR paper. Can you see that, Meg? On your screen.
I can indeed.
So
you might want to zoom in a bit.
Yes, okay, I'll zoom in a bit. Okay. So this is me demonstrating, not telling, but showing you how to do ninja question reading. So we are going to highlight certain keywords. And the first word that we're going to highlight is the word which tells us what the question is about. So what is this question about? If I zoom out again just a little bit so that you can see the diagram. Okay, so there's a picture of a bridge. Okay, so in the chat, please would you put what this question is about, do you think?
Give him a second to type.
Yeah, giving you a second to type. I'm going to pull up my chat on my extra screen here. Oh, it's so nice having two screens.
Ooh, centre of mass, moments and toppling, mechanics, moments, centre of mass.
Or
Emotion and forces.
topics overlap. Yeah, they really do overlap.
Plumb line experiment.
Ooh, plumb line experiment. Yes, absolutely. Okay,
Lots of different ones. I'm liking it.
So, you are mostly right. Okay, it is definitely about centre of mass. How do we know? Because the words centre of mass there appear on our in our question. Okay, so absolutely, it's about centre of mass. The other thing is that we've got two positions, so it possibly is about moments. But usually moments questions are things that haven't moved. So we are dealing with an object that's in equilibrium. Well, here we've got two different positions. So it might not be moments, but it might be. Whoever said mechanics, definitely maybe. What else might it be? What is important about the centre of mass? Okay, and can you see that we've got information about where the centre of mass is later on in the question. Now, obviously we haven't got a whole question here, but what is it that might be important about the centre of mass?
Well, we've got a whole bunch of questions.
Okay, so look, where
gravity,
the line,
GPE, weight.
Good. Okay.
Where the line of action is.
Now you're thinking about it. Okay, I like the GPE idea.
Where the weight of the object acts. I think that is per se.
Yeah,
Length.
absolutely. Yeah. Okay. So we've now beginning to get this idea that maybe the centre of mass and movement of the centre of mass when this object moves might be changing. Energy, maybe gravitational potential energy might be okay, so you're now beginning to think right now at this point when you're faced with a question. If you don't know how to address it immediately, then what you do is you go and you find the data sheet for the right set of equations that are relevant to the topic that you've now identified. So we've now identified that this might be moments, and it might be energy. It's almost certainly got to do with weight. It's almost certainly got to do with lines of actions of forces. Okay, so that's quite interesting, isn't it? Okay, so which set of equations would you pick? Now, I've got up here somewhere, no, insert, there we go, a data sheet. Okay, it happens to be an AQA one. Most people doing A-level physics are doing AQA, so I tend to pick that one. It starts off with the names for the constants and values for the constants. Then it goes on to look waves, and there they are. There's mechanics. Okay, so what I want you to do is I want you, whenever you are doing questions from now until your exams, the real ones, even if you're in year 12, you need to have a data sheet right next to you when you're doing A-level questions. Okay, that means that you basically need to have one on you at all times, and in your bag, in the front of your folder, on your desk at home, the dining room table, the kitchen table, your bedroom desk, wherever it is that you work, back of the loo door, so that you get so used to looking at it that it's second nature. Okay, so we've got the equations of motion, we've got energy, power, work, we've got efficiency. We've also got the equation for moment. There might be one or two others that are a little bit different. The ones that don't come up so much here. We do get F equals MA. Can you see that? F equals, I'm not in the right mode. Pen. F equals MA, but what you don't get given is the W is MG1. You are expected to remember that from GCSE. Okay, so you now have that open next to you. I want you to imagine. Okay, and now what we're going to do is we're going to go back, and we're going to have a little look at at the rest of the question. So the next thing we're going to do, having identified the topic and found the equations, we are going to identify the command word. What is the command word? The thing that tells you what to do. I'm going to let you put it in the chat. Oh, yeah. Yeah, you guys, you've spotted it. There we go.
It's so many describes.
Yes, it is describe. Okay, so you have to describe right now. One of the things that I want you to learn between now and when you do your exam is how to scaffold is the word. Wordy answers. So what their structures are. Okay, so for example, describe is you scaffold it this way, right? This is a 3-mark describe. Describe means say what you see. Or if you can't see it because it's too small, like it's happening in the nucleus of an atom or something, you say what you would see with your mind's eye. Okay. Now, that might be part of a process, depends what it is you have to describe. It might be a sequence of events, therefore, but it might just be a relationship between one variable and another. So you have to actually see what it is you are going to describe. So what are we describing here? Can you see it's how to find the centre of mass? So this is really saying what you would do when you find the centre of mass. Now, I'm hoping that most of you will have done this, but there is a caveat, an extra bit to this question. Can you see it says, including any equipment required? Right now, whenever a question asks about equipment, it's nearly always a good idea to draw a diagram and label it. You get credit for diagrams, and apart from anything else, it makes it easy for you to figure out what's going on. So I'm going to draw a clamp stand, which is how I would do it. So here is my clamp stand. I'm going to suspend my 2-dimensional shape from a piece of string. I'm going to suspend a plumb bob. I'm going to change colour. You can't do that in the exam, but I'm going to change colour. There's my plumb bob. Whoever it was talking about plumb bobs earlier. Oh, okay. So there's my plumb bob. I think my thing is not in equilibrium, my shape. But anyway, you need to mark in 2 places, don't you? Where doo-doo and doo-doo. Obviously, you don't use big fat blobs either. You use nice skinny little marks, and you draw between them with a ruler. And then what do? You turn it around and you suspend it from a different position, right? So you take all this off, okay? You turn it around, so I can't remember what my blobby thing looked like that, something like that. So you suspend it from a different position. Okay, there's my plumb bob. So I've already got one line on there that I've drawn between my 2 blobs. And now I've got another line, and I'm going to draw it between these 2 blobs. And where they cross, that's my centre of mass right now. It's a bit weird because I've got a sort of, it's slightly moon-shaped, my object. It is possible for the centre of mass not to be within the object. Just saying. But anyway, what would you do in order to describe this process? This is how you do it. So you literally say what you see. You would suspend your 2D shape. And the word suspend, not hold or grab, or it's got to be able to move, okay? And then what you've got to do is you have to also and a plumb bob, plumb with a B because it's plumb from plumbing, from lead. Plumbers used to use lead pipes. Plumb bob, okay, from the same suspension point. I can't bother to write it all out, point, okay? And then you wait for it to come to equilibrium. I mean, obviously, that waiting for it to come for equilibrium is unlikely to be in the mark scheme. This is only 3 marks, but in a 6 mark describe an experiment to show, you might want to put that in, okay? So you mark 2 points where, I can't bother to write it all out, mark 2 points where your plumb bob crosses your 2-dimensional shape, and then you join those 2 points with a ruler. So you need a ruler, a suspension point, so clamp stand or something. Okay, you need a plumb bob. You need some sort of a pen or pencil to mark, yeah? Can you see, there is the equipment. Can you see that I am not going to get all the marks if I don't write a list of the equipment? I mean, obviously, you're not going to write it as messy as I did on a screen with a pen that's too thick. But can you see, describe, say what you see. So you suspend your 2D shape, and then you mark the plumb bob, I can't say it, plumb bob line in 2 places. Join with a ruler. Okay, repeat, and then where the 2 lines cross, that is the center of mass. Can you see that this is what you've got to do in order to describe? Okay, so we have sussed question 1 right now. There is another really important thing about 19A. Okay, I'm going to clear my drawings. This is what I would describe as a signpost question. They've said, think about centre of mass. This question's about centre of mass. You're going to need to use the concept of centre of mass later on. What is the centre of mass? Can anybody tell me what the centre of mass is? If you were asked to define, that's another signpost question. Define the centre of mass of an object. What is it?
Where the weight acts, we have.
Yeah, it's not though, is it? Not
Massive centre, where the mass is concentrated. A point where the weight of the object appears to act.
Ah, like that one. Give him a star. Or her. Give it, right? We need, right, where the weight appears to act. Because, like I said, if you've got a moon-shaped object, the centre of mass is, I don't know, there. It's not even in the object. It's not where the mass is concentrated. That's not what it means. It's where the weight appears to act. Now, actually what's happening is every particle that this moon object is made from is being pulled down by gravity, okay? By the mass of that particle being pulled on by the gravity of the Earth, right? If you add up all those little vector sums, together, then you can replace all those little forces with one big force, which we call the weight, and it acts where it's where it appears to act. That is the center of mass. So it's not where the mass is concentrated, because there is no mass there in my moon-shaped object, so it's not that, and it's not where the weight actually acts, because the weight is really distributed amongst all the particles that make up this shape. So it's where the weight appears to act, okay, it's quite a subtle concept, just saying. So, but if you were asked to define centre of mass, that would also be a signpost question. It would say, this is about centre of mass, think about centre of mass, think about weight, think about lines of action of forces, think about. Okay, so let's move on to the next bit. Let's clear that. And then to move on to the next bit. So figure 19 shows a bridge. We've got a bridge that's raised by an electric motor. It's moving a section of the bridge. Right, now, when you have questions which have got numbers in, you need, in your Ninja question reading, to highlight all the numbers, okay? So we've got 14, we've got 6.3, we've got 1.3. Okay, We are told that it has a weight of 120 kilonewtons. Okay, we've got repeat of the 14 and the 6.3 actually in the question. Okay, and another thing that I think that it would probably be as well to mark is the pivot, which is there. Okay, so it's probably a good idea to mark pivot point, simply because this object is moving, it's turning about that point. Okay, right, now let's move on to the next bit and see what the question actually says. Calculate the average power required to raise the bridge to a vertical position in 90 seconds. Oh, look, we got another number. Okay, right, what's this question about? Topic, please.
Ready? Work done.
Yeah.
Energy and power.
Oh, there we go.
FV, electricity, power and energy.
I think it might be about power, don't you?
Electricity, work, energy, power.
Power
Power.
to the people.
Rate
Right.
of energy transferred, and someone
Good.
put power.
Yeah, absolutely. Rate of energy transferred is power. Okay, power is joules per second, so it's the rate of energy transfer. Absolutely. So it is power. I mean, obviously, work matters because work is energy. I mean, it's just another expression for the term energy. So work is related to power, and then 90 seconds obviously becomes important, doesn't it? Okay. So what's the command word? Calculate.
Yes, Brian.
Yeah, calculate.
Another calculate.
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 Right, okay, so calculate, absolutely calculate is the command word.
Calculate in all caps.
Excellent. Okay, so we now know that we're going to calculate power. Find your equations. If you've got a spare place to put them, pop your equations there, right?
E over T equals P, or P equals E over T, or P equals W over T, P equals FV.
Right, there are lots of them. So we've got power is a rate of change of work done.
Whoops, we've got P equals W over T.
Yeah, work over time. Yeah, absolutely. Okay, or power is the force times velocity. Okay. Okay, so
well, we've got P equals IV.
Oh, P equals IV is of course an expression for power, but that's in an electrical system. Now, I
mean, this
is an electrical bridge.
Yeah.
But we haven't got any electrical information, have we?
No.
So it's a good thought, and maybe in another question, it might very well be relevant. But in this particular question, because we've got no information about any electrical stuff, we're going to say no, it's not that one. So we could use either of these. If we use the first one, then we need work, because we got the time in our question, haven't we? The 90 seconds, remember? That was why we slowed down. That was why we used our highlighter to highlight the number 90 seconds. So that when we're thinking about this, looking for our equations, we're thinking about equations which got time in. Okay, so let's think then, if we're going to use that equation, power is energy over time, or work over time, then power is work over time. This is dW by dt, but it's work over time. What work equation might be relevant here? What's the equation for work? This is not weight, this is work.
We've got W equals FD, W equals FS cos.
Yeah, right. Okay, so this is the GCSE equation, and this Fs cos theta, that's the A-level equation. Okay, now the only difference between them is that in the A-level equation, we're just making sure that our force and our displacement are parallel to each other. Okay, so what we need to think about then, the work done is the force, which is the weight in this case. That's what we're doing work against, the weight pulling down and we're lifting it up. The force times, it has to be the vertical distance, because it's the component of S, which is in the same line of action as our weight. So it's the vertical component. So the fact that the bridge tips sideways as well, irrelevant, makes no odds that it goes sideways as well as up, because there is no force stopping it from going sideways. So there's no work done when it moves sideways.
I disagree.
Friction. Well, okay. We're going to assume there's no friction.
Spherical chickens in a vacuum.
Yeah, we have to assume there's no friction. The A-level physics questions are too difficult. If you are clever enough to realise there's always friction, and you can't do questions if you think there's friction all the time. So you have to bear in mind that most of the time there's no friction. Right, okay. So what we're going to do is we are going to choose this equation. We're going to make sure that we're only using the vertical distance. So it's sort of this one, but we're using the GCSE equation. So, okay, so our equation then is going to be work is force times distance, and power then is the work, which is force, which is the mg, which is the weight, times distance divided by time. And I'd like to point out that those of you that said mgh are absolutely right, because h is the distance upwards.
Height.
So can you see this becomes power is equal to the potential energy over time. It's mgh over time. So you just plug the numbers in. I'm not going to do it. Actually doing it's boring. Right, okay, so the next bit then, suggest why the actual electric motor used to lift the bridge has a maximum power output several times larger than the calculated value in BI. Okay, so why is it going to be larger? Come on, we've got 1 mark. 1 mark. And the command word here is... Yes, well done. Suggest.
And someone said before you even asked is it is not 100% efficient.
Good. Not 100% efficient. What does that mean? If things are not 100% efficient, usually what sort of energy is getting wasted?
Oh.
Thermal energy, yeah, heat, which is as a result of
light.
Work done against friction.
And we've got light coming on as well.
Oh, I don't think this bridge is going to light up.
If it gets hot enough, it might.
It is true that friction can cause light to come out. So if any of you have ever watched rally driving, where they use their brakes a lot at night, the brakes glow red hot.
See the calipers.
Yeah, well, not the calipers, the discs.
Well, the calipers will also...
They're holding the pads, but you can't see them because they're dark. But anyway, it doesn't matter. Right, okay. So right now, we have done this question. The point was not to do the question. It's actually a relatively straightforward one. The point was to show you how to use the ninja question reading. Can you see? Now, I know I've gone through it very slowly. So let's see if we can use the ninja question reading in the next question a little bit more quickly. So the next question that I was going to do was an AQA one, and I am going to get the year 12 to answer a year 13 question. So right, the first thing to do is to spot that question 3.1 is a signpost question. The signpost question. Okay, what is signpost? What is the question about, people?
Capacitors.
It's about capacitors. So at this point, what do? You go and you find your capacitor equations. Look them up.
Look at the formula book.
Yay! Okay, so we're looking at the formula book. Right,
Someone's already put charge per unit volt.
Okay. Capacitance, yes, absolutely. That's the definition that we actually have to use.
C equals Q over V.
Right, capacitor equations, where are they?
Charge per PD.
Nuclear, have I gone past them?
Oh, 370
I've gone past them. What have I done?
Per 1 volt. Interesting.
Yeah, no, that was the answer to the question.
Oh, damn.
That's really good.
Yeah.
Oh, there they are. Right, capacitance.
Oh,
right.
Someone else has already answered as well.
Okay, so we want any equations which have got C in. Okay, so those two, those ones. Oh, okay, so quite a lot. Okay, I'm just going to jot these down. C is Q over V. We've got C is A, epsilon naught, epsilon R over D. Now, if you are in year 12, you're going, I don't know what any of this is about.
Big scary.
Yeah. Doesn't care. Doesn't matter. Okay, all you need to know is what the symbols mean. Okay, if you know what the symbols mean, then you can do this. Okay, we got Q is equal to Q naught e to the minus T over RC. And there's one more, the time constant, right? T is a curly T, it's called a tilde. It's a Greek letter, RC. Right, okay, so this one, I'm just going to put it, I can't spell. Time constant does not begin with a P. Time constant.
Time.
Like pterodactyl. Right, okay. So we are now going to answer the first bit. What is meant by a capacitance of 370? Right. I'm just going to make you, with your Ninja highlighter pen, highlight the number. Notice that there's a number. You cannot define a capacitance of 370 microfarads without mentioning the number. If you do, you will not get the mark. You can define capacitance without a number, but you can't define 370 microfarads of capacitance without the number. Okay, so you absolutely have to put the number in this answer. And the clue that says that you've got to put the number in this answer is the number. Okay, so please notice your numbers. Right, so, and this one defines capacitance. So that's what we're going to do. We're going to define our capacitance of 3. Right, so it means, okay, so a capacitance of 370 microfarads means the object can store from 370 micro, that is charge, coulombs of charge per, that is volt. Okay, so a capacitance of 370 microfarads means that the object can store 370 microcoulombs of charge per volt. You must put the number in. Okay, so we've done 3.1. But now what I want you to do, especially if you are year 12, is I want you to figure out how to do 3.2. Okay, Ninja question reading. What are we asked to do? Where is the command word? What have we got to work out?
Oh boy, here we go.
Excellent.
Calculate.
There it is.
Resistance.
Okay.
Resistance. Calculate. What?
Okay, so we are expected to calculate the resistance. Okay. So now what I want you to do is to look at the equations that I've written down. Okay, I am going to say that the resistance has got the symbol R. Capacitance has the symbol C. T is time, V is voltage. What else have we got? E is energy. This thing, that is the time constant, which is why I wrote it on the other side. Okay, so I want you to find what equation we can use to work out R. So you're looking for an equation with R in it, because that's what we want. And what else have we got? This is why you have to highlight the numbers. We have the capacitance. We have a voltage. We have a time. We have another time. Okay, the time constant. Okay, so which equation has got R in it and some of the other things that we've got? Okay, so it's this time constant one. It's on the data sheet. You don't have to know anything about capacitors. The equation is on the data sheet. As long as you know what the symbols mean, even if you know nothing about capacitance, you can read the words time constant and the fact that it's RC. You can read the capacitance. You've just defined the capacitance. That's a signpost. This is about capacitance. In fact, it's about this capacitor. So we absolutely use this equation. We need to rearrange it so that R is the subject of the equation. And then we need to substitute our values in. 1 second for the time constant and 370 microfarads. Micro is times 10 to the minus 6. So put your numbers into your calculator. I'm actually going to do this one. 1, and if you can beat me, you can have a gold star. Divided by 370.
Well, we've already got some answers
10 to the minus 6. Well, well done. Lots of gold stars then. So I get 2,702, but I'm not, or 3. I'm not going to do it to that many significant figures because it's only 2 significant figures in the question. Okay, so, and its symbol is ohms. We're given this in this question. Right, now that was the point that I was trying to make. You do not need to really understand a question sometimes in order to be able to do it. Okay, do not be dismayed if you go, okay, do the ninja question reading. What's it about? What's your command word? What symbols have you got? What equations are there that's relevant to the topic that you've identified? And then even if you're in year 12, you can answer a question on capacitance. You've got no clue what the time constant means.
I have a question.
Yes, a question.
Will you use a capacitance of 370 microfarads or 0 because the capacitor is uncharged?
The capacitance is not the same as the charge. Capacitance is C, charge is Q. Capacitance is a property of an object. So it's like resistance. A resistor doesn't have no resistance just because there's no current flowing. So any object has a capacitance. I've got a capacitance. A Bunsen burner has a capacitance. This little dragon has a capacitance. Okay. It's not a very high capacitance because this little dragon isn't designed to store charge. Trampolines have got really quite a lot of capacitance, which is why when you jump about and you do, you get a lot of static electricity stored, a lot of charges stored, and then you touch your swing when you're getting off. Shock. Okay, so and the capacitance is a property of the object. Okay, charge is something that it might have or it might not have, but the capacitance is a property of an object, just like resistance is a property of an object or mass is a property of an object. Okay, right. I've done that one. Right, we want to move.
I have another question about the capacitance.
Okay.
Sorry, typing and speaking at the same time doesn't work. Will forming a circuit with an oddly long amount of wire be the same as having a capacitor?
Mostly no. The essence of a conductor is that the charges are free to move. Certainly in A-level physics, we do not allow, in our regular circuits, like the one that's on the screen right now, we do not allow for any resistance of the wires. We assume that they have zero resistance. So unless you've got literally miles of wire, you cannot use that as a component in your circuit. Not unless it's a resistive wire. If it was a resistive wire, then it would be a resistor, not a capacitor. Resistors are not designed to store charge. They do allow charge to flow, but they resist how much the charge flows. That's the essence of this resistance. So no, wires are not used as capacitors. Capacitors are parallel plates. And what happens is that usually the plates are flexible and they put something between the plates that will prevent charge from moving from one plate to the other. And it's usually in the little round sort of cylindrical capacitors, it's usually an oil impregnated paper actually. And then you wrap those plates up into a sausage. Like you're rolling up a sleeping bag, and then you attach legs, one to each plate, and that is a capacitor. I mean, you put it in a package and everything, but that's a capacitor. The capacitors, they have this thing called a time constant. It takes time for them to charge and to discharge, depending on the resistor that is in the circuit with them. That's why the time constant is R times C. And so capacitors are used in timing circuits in order to answer Elise's question. So they're used in timing circuits. Those of you that had Christmas tree lights, little LEDs all over your Christmas tree, and they're flashing on and off, and lots of them come with a little box, and you can twiddle a knob on the box and you can set them to different settings, and you can have all the red ones on and then all the green ones on and then all the blue ones on, and then in between the red ones go off when the green ones are on and the blue ones are on, right, or whatever, right? The timing for setting the time, it's all capacitors and resistors. So capacitors and resistors are used for timing circuits. There is one actually other really interesting thing about capacitors. Again, it's got to do with timing and charging and discharging. But if you have alternating circuits, then because the current keeps changing direction, the capacitor charges up and then discharges, charges up and then discharges, charges up and then discharges. And so if you combine a capacitor with something called an inductor, which is just the name for a resistor but in an alternating circuit, you have control of how long it takes to charge and discharge. And when you do that, then you could, if you change the frequency of your circuit, how much it's, you know, the alternating bit, if you increase or decrease the frequency, you can set up resonances. So those of you that are in year 13 and have done resonance with simple harmonic motion, alternating circuits are simple harmonic, and you can have a circuit that resonates, and that is how you tune, or in the old days, you tune a radio. You change the capacitance with your tuner. You literally turn the plates so that they interlock from one another. So you change the resonant frequency of the tuning circuit, and then you amplify that one frequency. So you can pick one frequency out of all the radio waves that are passing through the air and past you all the time. You can pick the one frequency, amplify it, send the signal out to a radio or to a speaker, and there you got radio. That's how analog radio works. So tuning circuits, really important, not part of your A level. Right, okay. I'm going to move on.
And capacitors can keep lights on even after the thing's turned off.
So, for a short while, yeah. I mean,
kind of go, yeah. Once you unplug it.
Yeah, when you unplug something, especially an old-fashioned charger, like I've got my I mean, it doesn't have an LED on it, but I've got an old-fashioned charger. This is for my laptop that I'm looking at you on. And some of these have got like an LED that says, I'm on. And when you unplug it, it doesn't go off immediately. It goes, and eventually it goes off. And that is the capacitors inside the system discharging. Okay, right. Okay, let's move on. We're taking too long on this. Right, I want to go on to the next bit. Right, so the next bit, if you remember, is I can't remember. Oh yes, there we go. Okay, so some questions you just need to learn. Okay, the ones you need to do enough questions that you recognize the ones that keep on coming up. This one, explain how a standing wave is set up. It's going to come up. It will. It comes up every year. So you might just as well learn it. I mean, this is a 6-mark explain. And if you know it, 6 free marks. Ooh, that might easily be a grade. Just go away and learn it. So if we look at the mark scheme for this, it's horrible. Okay, so they now split it not into 6, 5, 4, 3, 2, 1. They now split it into 6 and 5. That's a top grade mark. 4 and 3, that's a middling, and 1 and 2 is the lower end. And they have